In this lecture, I am going to consider the numerical solution of algebraic and transcendental equations using a very robust method which is called as Newton-Raphson method. Right here, I'm going to make use of the Taylor series expansion of an equation. So here I assume that let f of x is equal to 0 be the given equation, right? And my improved root, I call that as let xi be the exact root of f of x is equal to 0. What do you mean by that? That is f of xi is equal to 0, right? I take x naught as my initial approximation. Now, I let x naught is or be the initial approximation. And h be the difference between xi and x naught. That is, xi is equal to x naught plus h. I call this as equation 1. Right. Now, I make use of the Taylor series expansion. So we know that by Taylor series expansion of f of x around x is equal to x naught, we get f of x naught plus h is equal to f of x naught plus h times f dash of x naught plus order of h squared terms. So the next term will be h squared by 2 factorial f double dash x naught plus h cubed by 3 factorial f triple dash x naught. So like that it continues order of h squared, neglecting higher degree terms in h. We can write above equation as f of x naught plus h is equal to f of x naught plus h times f dash of x naught. Right. So, but from equation 1, xi is equal to x naught plus h. Therefore, and we know that f of xi is equal to 0. So hence f of x naught plus h also is 0. Therefore, 0 is equal to f of x naught plus h times f dash of x naught. This implies h is equal to minus f of x naught over f dash of x naught. So using this in equation 1, we get xi is equal to x naught minus f of x naught over f dash of x naught. So this is expression 2. Equation 2 suggests that equation 2 gives the next improved root x1 of f of x is equal to 0. That is x1 is 1 by is given by x1 is equal to x naught minus f of x naught over f dash of x naught. Similarly, we can find x2, x3, so on as xk plus 1 is equal to xk minus f of xk over f dash of xk. K is equal to 0, 1, 2, so on. If I put k is equal to 0, I get x1. x1 is x naught minus f of xk over f dash of xk. If I put k is equal to 1, I get x2 is equal to x1 minus f of x1 over f dash of x1. If I put k is equal to 2, I get x2 plus 1, that is x3 is equal to x2 minus f of x2 over f dash of x2, so on. So I call this as expression 3. So equation 3 is the formula of Newton-Raphson method. Right. It converges to the root. Nowadays, it is uh, frequently used, or it's a popular method. It converges or it approaches root faster than false position method. In the false position method, we arrived at the formula by considering the chord at which the x-axis, sorry, the point at which chord cuts x-axis, chord joining A, f of A and B, f of B. Here also, I will give you the geometrical meaning. So we can arrive at Newton's method geometrically also, geometrical meaning. What I will do is, I consider a function, let f of x is equal to 0 be the given equation, right? So now what I have to do, let's consider graph of the function y is equal to f of x. Right. So I draw the graph of the function now. So let this be the graph of the function. Again, as you know, make sure that in that interval the root lies. So this is my A. Let this be my B. So that A f of A, B f of B. So this is my B. So that here the root is the value of the function is negative. This is A f of A, and here it is B f of B. So here A f of A is positive, B f of A f of A. F of A is negative, F of B is positive. So I consider any point here x naught because in this interval the root lies. So I consider any point x naught. This is my x naught here, right? So now I draw the tangent. I draw the tangent to the curve y is equal to f of x at x naught. So this is my tangent, right? So at this point x naught, I draw the tangent. I consider the next improved route as the point at which this tangent PT cuts x-axis. This I call as x1. This is PT. This tangent is PT. Right? Now, right? Now, what is the equation of tangent? See, this point is what? It is x naught f of x naught, right? What is equation of the tangent for the curve at x is equal to a? What is equation of the tangent? So what is the slope of the tangent? It is f dash of x naught, right? So I make use of the equation of the line passing through x naught, f of x naught, and having the slope f dash of x naught. That is the idea because we have already studied these things in uh, the higher semester, means the previous semesters, the geometrical meaning of geometrical meaning of the differentiation. So now, slope of the curve, let A and B be the numbers with A less than B such that f of A and f of B are of opposite signs. Opposite signs. So now I am choosing A and B just to make sure that there is a root. So with this ensures that a root lies in interval AB. Right. So let us consider any point x naught in this interval as shown in the figure. As shown in the figure. Right. Now, I consider this one, this figure, I keep it for my reference. So I consider, I consider this figure now because this figure is required. Right. Now I draw the tangent PT at x naught f of x naught. Let P be the point on the curve. On the curve y is equal to f of x. That is this curve. This curve is y is equal to f of x. Right. Now draw the tangent. Draw the tangent PT at P. Right. The coordinates of P is given by x naught f of x naught. Correct now? This point, the x value is x naught, the y value is f of x naught. And also, we know that its slope is given by f dash of x naught, because this is the geometrical meaning of differentiation, that is dy by dx. Hence, equation of Pt is given by y minus y naught is equal to m times x minus x naught. That is y minus f of x naught, because y naught is f of x naught, is equal to m is f dash of x naught times x minus x naught. So this is the equation of the tangent, right? So this is the equation of the tangent PT, right? So because it passes through x naught y naught, so y naught is f dash f of x naught, and it is having the slope f dash of x naught. This is the slope m. This is my m, the slope. So I make use of this, right? Now if you look at this, see, I take x1 as the point at which this tangent PT cuts x-axis. Let the improved route x1 be the point at which tangent PT cuts x-axis. That is, it cuts x-axis at x1, y value will be 0. Therefore, hence, the above equation gives the y value is 0 minus f of x naught is equal to f dash of x naught times x1 minus x naught. So x I replaced by x1, y I replaced by 0. So if I simplify this, this gives x1 is equal to x naught minus f of x naught over f dash of x naught. So this is my Newton's method formula for x is equal to x1. So thus, now what is the inference? So in false position method, we considered the chord to arrive at the false position method formula. So on the similar lines, what we can say, thus in Newton-Raphson method, the improved route is taken as the point at which the tangent drawn at x naught cuts x axis. So this is the geometrical meaning. That is, we can arrive at the Newton-Raphson method formula by considering the point at which the tangent cuts x-axis as my next improved route. So this gives me the same formula. Therefore, here we considered the tangent, and in false position method we considered the secant. Naturally, this Newton-Raphson method converges or goes to the exact route much faster than the false position method. So we are going to consider the problems from the question bank. The problem is, I'll write the problems now. I consider the problem. Just a minute. What the problem says is, uh, solve the following equation. That is question number, and I'll just go down that it is question number uh, 11. So question number 11, what it says is, in the question paper, it is question number 11. I take the example of the example from the Newton's method. What it says is, using Newton-Raphson method, find the real root of the equation. Hmm, it is x sine x plus cos x is equal to 0. Here x is equal to pi. That means he has given, take x naught is equal to pi. He has already given the value of x naught. X naught is equal to pi. So now we shall solve this problem. So I consider Right. I consider the problem now. Uh, so this will be equal to, I consider, so this problem gives me f of x is equal to, right? I, so this gives me the case f of x is equal to, right? So now, so this gives me what is f of x now? So solution. First, I have to find out the iteration scheme now. The Newton-Raphson formula is given by is given by xk plus 1 is equal to xk minus f of xk over f dash of xk. Right? K is equal to, it starts from 0, 1, 2, so on. Right? So now I derive f of xk over f dash of xk. Now f of x is what? The right hand side of the equation. So the equation is what? It is x, the equation is what? It is x sin x plus cos x. So f x is what? X sin x plus cos x. So if this is f of x, what is f dash of x? So f dash of x will be what? It is differentiation of x sin x. So x times cos x, differentiation of sin x is cos x, plus differentiation of x is 1, so into sin x, then differentiation of cos x is minus sin x. So x sin x differentiation will be what? X times differentiation of cos x plus x differentiation of x is 1 times sin x minus sin x. So these two cancel. So f dash of x is equal to cos x. Right? Therefore, xk plus 1 will be equal to what? It is xk minus f of xk. It is wherever x is there, replace that by xk. So xk sin of xk minus cos of xk divided by, it is xk cos xk. Right? So if you simplify this, you can simplify this further. You can make the life simple. So this is what? This is Newton's forward difference, Newton-Raphson method, right? I have, what I did, this f of xk, I replaced x by xk, right? Then f dash of xk, I replaced x by xk here. If you want to make the life simple, I can still simplify it, and I can write this as, that is mm, xk plus 1 is equal to, I can write this as xk. I take individual term here. It is xk sin xk over xk cos xk. Then it will be plus cos xk over xk cos xk. That is, I separated these two terms. So here xk cancels, cos xk cancels. Therefore, my iteration scheme will be xk plus 1 is equal to xk minus tan xk, then plus 1 by xk. So this is my iteration scheme, right? So now take x naught as a pi. He has already given that. Taking the now take x naught is equal to pi. So x1 is given by what? It is x naught minus tan x naught plus 1 by x naught. So therefore this is equal to pi minus tan pi plus 1 by pi. So x naught is pi, right? So if I put the value of x naught, 3.14159. So what is the value of pi? Pi is 3.14159, correct up to, means it is the root nearly equal to, I can say, is up to, correct up to 6 decimals, right? Rounded off to 6 decimals. So if I find out the value, I get x1 to be 1.2.8328. If I use this one, x2 will be what? X2 will be x1 minus tan x1 plus 1 by x1. So I use this value here. See, I use this value here. So what I get? X2 will be equal to, if I simplify this, 2.7986. If I, like this, if I find out x3 will be what? X2 minus tan x2 plus 1 by x2. So that will be equal to, for this value of x2, 2.7986, x3 will be 2.79839. Similarly, x4 will be x3 minus tan x3 plus 1 by x3. If I simplify this, if I find out, so I get 2.79839. I'm getting back uh, 2.79838. Therefore, the root correct up to 4 places is 2.79838. So like this gives me the root. This is how we use the Newton-Raphson method to find out the real root of the equation. It's a very modern method. It gives the solution much faster than the new false position method. So with this, we completed the solution of numerical solution of algebraic and transcendental equations. And we are going to study the integrations, integration or numerical integration in the next lecture.